this. So good news for you is it's not going to be brand new. You'll be able to get through this fairly quickly. We are switching textbooks as well. So means not as much, but I do have lots of textbooks, so I probably should have handed those out. So we're looking at electric charges now. Where we end up getting to, or where we're coming from, is this actually starts when it talks about forces. When we do forces so far, we've talked about forces equal to mass times acceleration. We looked at
interruption. Lexi, Harlock to room 23, please. Lexi to room 23.
Mrs. Inspies.
So we talked about forces, we talked about net force. Now we're going to talk about force between electric charges. Now, everybody at some point has walked along a carpet, maybe in the library, reached for the knob on the door, and all of a sudden, spark. You get a shock, right? These chairs are great for it too if you've got static in your clothing. You rub along, and if you touch the metal pole, you get a shock again. Well, we're going to look at where all of this comes from. Those are called static charges. And we're going to look at how do we transfer charges from one object to another. We look at lightning, and we'll just discuss it. But where we're going to get at is, can we calculate what the force is between two charges? That's more or less the big end game for us in this. In this unit, you're going to have actually some theory questions in which you have to you'll have to do some reading out of the booklet that I've given you, and you'll have to answer questions on the test based on theory. It's the first of 2 units in which we do theory questions. So read with me on this. I'm just going to go through the main points. Starting with charges at rest, we can observe about us number of physical effects that are sometimes produced by rubbing pieces of dry matter. Sometimes an annoying shock is felt when the door handle of an automobile is touched after one slides over plastic-covered seats. We may feel a shock after we walk on a wooden carpet and then touch a doorknob or other metal object. The slight crackling sound heard when the dry hair is brushed and the tendency of thin sheets of paper to resist separation are other common observations of these physical effects. When an object shows effects of the type we have described, we say that it is an electric charge. The process that produces electric charges on an object is called electrification. Okay, so if you want to just highlight, I'm going to give you a list of words that we want. And so electrification is a process by which we charge something. How many of you have taken a balloon, rubbed it on your head, stuck it on a wall? Anybody done that? How many of you taken a toque off and rub your toque in the dark to see all the sparks? Okay, that's what you're doing. You're producing what we call electrification. You're producing a charge in it. Electrification is most apparent when the air is dry. An object that is electrically charged can attract small bits of cork, paper, other lightweight particles. Because the electric charge is confined to the object and is not moving, it is called electrostatic charge. Thus, static electricity is stationary electricity in the form of electric charge at rest. So, static electricity, static means at rest. So we have static electricity all around us. But generally, until we move it towards something else that's actually has an electric charge on it, nothing really happens. But the moment that you come close, if you by chance come close to that doorknob, it's not the point where you touch it, it's at the point where the electric charge can transfer from you to the doorknob or the doorknob to you. There are 2 kinds of charge. We can detect the presence of an electrostatic charge by means of an instrument called an electroscope. Basically what you need to know is if you flip over, it's actually 2 pages in, we need to know the 2 types of electroscope, but we'll worry about that after. Okay, so producing electric charge. I'm going to pull up my bag of toys here. Yeah. Oh.
We're shocked that you guys want to touch the laundry machine.
Okay. Here is my pit ball. Oh, there we go. Better. Okay, first off, just gonna tie this pit ball up here. It's just something that produces an easy charge on it. Now, okay, so I have a glass rod right now. And what we're going to figure out.
Nick, or go to the office. Nick, to the office.
Oh, found that guy today. Okay, so I'm going to rub fur on a glass rod. And so if you're actually reading in the book here right now, it says the electric charge produced on the rubber rod. Oh, I forgot the rubber one instead of the glass one. The electric charge produced on the rubber rod when it is stroked with flannel or fur is called negative. The rod is said to be charged negatively. The electric charge produced on the glass rod when the rod is stroked with silk is called the positive charge. So, if I use the fur has electrons inside it. And by rubbing it on the rubber rod, I have created an electric charge of that's a negative charge. It means I have more electrons than protons in my charge. Now, as I move it towards the pith ball, you can see it's moving, and it's moving towards the rod as I move it towards it. So what charge is on that pith ball then if it's moving towards my rubber rod in which I put an electric charge of a negative on it? It's got to be a positive because unlike charges attract each other. So as it moves closer, okay, it's not moving very much. Let's see if I can create a bigger one. As it moves closer to it, it's going to attract to it until the point where it touches. Now that it's touched, you can see it's touching here. Now, the electrons that I charged from the fur and transferred to the rod are now transferring from the rod to the pith ball. So that pith ball now has an electric charge of a negative charge on it. Now as I bring this closer, it's pushing it away because now they have the same charge on it. Okay? And that's simple electrostatics. Like charges unlike charges attract, like charges repel each other. What I'm doing is I'm inducing a charge of a negative on this rod. So now I'm assuming now then that the pith ball, well, it's lost its charge. I'm going to charge it again, make it a negative by touching it. Okay, so now it should push away, which it's doing. It's pushing away from it. Okay, now if I take a glass rod now, I don't have any soak in here. So these places I need these phones on. Okay, now it should attract to it. Okay, because when I use, now, so there's two things that you want to highlight in there. When you use fur on a rubber rod, you're inducing a negative charge on it. You're transferring electrons to it. When you're using silk or cloth on a glass rod, you're inducing a charge of a positive on the glass rod. But if you are aware from chemistry, positive charges don't actually move. The only thing that moves is the electrons, the negative charges. So basically, bless you, what you're doing is you're either adding negative charges to make it a negative, or you're taking the negative charges out. So by rubbing this glass rod, I'm taking the negative electrons out of here and putting them into the silk. And at that point, I've now got it repelling because they are now the same charge again. Okay, so in that little paragraph there, it says electric charge produced on the rubber rod when the rod is stroked with flannel or fur is called a negative charge. Okay, and then the glass rod produces a positive charge on it.
So where does it say about the glass and the top?
Right here, right in the middle.
Okay, I made that into a box here.
Okay, so it says, you
Show
see it?
this again,
Yeah, you're good? Okay, so The next most important thing is at the bottom here, and that's this. Basic laws of electrostatics. Okay? The observations are summarized in a basic law of electrostatics. Objects that are similarly charged repel each other. Objects that are oppositely charged attract each other. Okay? That's the basic laws of electrostatics. So it goes on and it shows you in the diagrams in figure 16.2 at the top of the next page how two pith balls hanging, if they're both negatives and both positives, they repel each other. If they're opposite charges, they attract each other. I want to look at it something like, just for a second here. If I have a neutral object, a neutral charge, okay, that means that I have the same number of electrons as I do protons. So to create a positive charge on a neutral object, I have to take the electrons away from it, so that there's more positive than there are negative. To create a negative charge on something, I have to put electrons into it, so that I have more electrons. Because the positive protons do not transfer. They stay as is. It's only the electrons that move. Now if you're doing chemistry, where are all your electrons found? They're in orbits outside, right? On the outside of it. So they're the only ones. So in the first shell there's 2. The second shell there can be 8. They're the only ones that can move. And that's how you change your charges in chemistry to look at when you're using ions. So it's the same exact thing.
Gentlemen, they're in room 7. Gentlemen, in room 7.
Okay? Alright. Let's keep flipping here. The electroscope, page 383. Two types of electroscopes. So an electroscope just measures, but not quantitatively. It just measures the charge that you have. So I can't really say it measures, but it finds the charge that you have and it shows you whether you have like charges or not. So two common types of electroscopes that are more sensitive than simple pith ball device are shown in figure 16.3. So you have the vane electroscope, which consists of a light aluminum rod mounted by means of a central bearing on a metal support that is insulated from its metal stand. When charged, the vane is deflected at an angle by the electrostatic repulsion. The angle of deflection depends on the magnitude of the charge. So there's that little arm you see in the aluminum vane. It will move once the metal knob has been charged on it. A leaf electroscope consists of very fragile strips of gold leaves suspended from a metal stem that is capped with a metal knob. The leaves are enclosed in a metal case and with glass windows for their protection. The metal stem is insulated from the case. So the two leaves will just move away from each other on it. So they show it on page 384. Excuse me, figure 16.4. A charge is conducted to the electroscope by copper wire. Okay? So you need to know the two types of electroscopes. That's basically it. I'm basically going to go through all the theory stuff with you quickly because you're going to get questions on it and then you can go back and do it a little bit in more detail. Conductor and an insulator. Do we know the difference between a conductor and an insulator? What's a conductor? It can store or transfer electricity, right? So what's a type of a conductor? What's a good conductor? What's that? Any metal? Yeah. Okay, what else? Anything else? A good conductor? What'd you say?
Water.
Yeah, water is a very good conductor as well, obviously. Hence we don't put anything that's plugged in a sink, right? Insulators, types of insulators.
Plastics, glass.
What's that?
Glass and plastic.
Yeah. What's it better? What's the
Rubber.
ultimate insulator?
Rubber.
Rubber, right? So rubber has no ability to pass electricity or electrons through it. Okay, so conductor is the material through which an electric charge is readily transferred. An insulator is a material through which an electric charge is not readily transferred. And so on. Okay. The next bit is transferring electrostatic charge. Okay, when I took the glass rod and I moved it towards the pith ball, the pith ball came towards it, sorry, the rubber rod, the pith ball came towards it, and once it touched, I did what I call induced a charge on the pith ball. So it was temporarily had an induction of charge on it. I put an electrons into that pith ball and I induced a charge. That charge was temporary. As soon as I moved that rubber away, after a bit of time, it no longer was negatively charged. It went back to a neutral charge on it. So you can induce a charge by simply bringing it close towards it. Now, the one thing I like to show that demonstrates this, because we are going to get into magnification, because electricity and magnification actually go together quite well. The largest magnets that we ever deal with are electromagnets, in which you wrap the magnet in electric wire, and it creates it. So I'm going to temporarily induce magnification on this nail. So right now, I have a paper clip on here, and no way that this nail is going to pick up that paper clip. Okay, there's no magnification on it. The same way as I had no charge on that pith ball. So the moment I put that, I need a bigger magnet. The moment I put the magnet onto, get the big wheel one. The moment I put the magnet and I attach it to the nail now has magnification, and it can now pick up the paper clip. So I'm inducing magnification on the paper clip. Now, what will happen if I release the nail from the magnet? It should fall, right? But it actually maintains the magnification on it temporarily. Okay? The same thing happened with that pith ball. I transferred those electrons into that pith ball, and it actually had an electric charge. And now it's gone. So now I go back to it again, and I can't pick it up again. It has to have the magnet do it, and it picks it up again. Okay? So we actually get into electric fields more so in grade 12 than we do in grade 11, but it helps to see that demonstration as an actual very similar demonstration to with the electrons and their charges being transferred. So 16.6, transferring electrostatic charges. It's a lot of writing in here. It just talks about bringing it closer. If you look at figure 16.7, I like this figure. So I take a metal rod, okay, and I have charges all the way through this rod here. And they're all kind of shuffled through there. Now, the moment I bring a rod in towards it, that is negatively charged. So I've rubbed this rod with fur, and I've induced a negative charge on it. As I bring it closer, what happens here, and again, this is another thing that happens in the domain of magnification as well, is all of the positive charges are going to be attracted, and they're all going to realign. So they'll end up realigning right here, all the way along here, and my negative charge is going to repel. So my negatives all end up coming onto the outside of this. So the closer I get this rod towards it, okay, this is going to happen. Now, what happens then is the negative charges from here are going to be placed on to here. Therefore, this is going to take over a negative charge from it, because only the negatives move. So these negative charges are going to move in here, and they'll transfer, and you'll end up with an excess amount of electrons in there, which creates a negative charge. So this charge is called conduction. A charge can be transferred by conduction. If we touch the knob of an electroscope with a negatively charged rubber rod, it says the leaves diverge. That's at the top of the page. When the rod is removed, the negative charges will remain inside of here. Okay? And we refer to that as a residual charge. So if you look at 16.7, this is on page 387, talks about a residual charge and how it remains inside here even if I move the rubber rod away from it. All right, let's go to page 388. This is the math part of it. All right, so this is very, very basic electrostatics, probably something that you studied grade 9, grade 10, okay, there'll be a little bit of this in it. Where it brings it into a grade 11 is talking about our ability to calculate the force between charges. Okay, so first things first, if I have a charge, so I have what we call any individual charge is called a point charge. And around that point charge, you have an electric field. And you have force around it. So inside this point charge, or around this point charge, I have an electric field around it. So that's why if you're around the knob of the door, you don't actually have to touch the door, because you just have to enter into this electric field where that charge is before it actually gives you the shock. Okay? So what happens then to these lines of force that surround it if I am to bring another positive point charge towards it? Okay? So, my poor attempt at drawing. Alright, so as I move this guy closer, what's going to happen to the lines of force? Are they going to attract each other, or are they going to repel each other? They're going to repel. So these force lines are going to go up like this. And the force lines from this guy are going to do the same. They're going to come away from each other. But that still has, because of gravity, we still have a force pulling them together. Even though the lines of force are pushing apart because they're like in charge, there's still a force that attracts between the two of them. So the first equation that we deal with is, the first thing that we need to know is charge. How do we measure charge? So I better do that first. So take a look on page 388. What is charge? Coulombs. That's right. Okay, so what is 1 coulomb though? Alright, so now, we talk about electricity as a transfer of electrons, right? So 1 coulomb of charge has 6.25 times 10 to the 18 electrons in it. Okay? So 1 coulomb is what we measure charge in. Alright? And then we go from coulombs, we go to coulombs per second, which is an ampere. And then after you do an ampere, we work into joules of work, which is also current. So we just keep building from this. This is our most basic building block that we're going to work with right now. Now, if I work this in reverse, the charge on 1 electron, okay, is 1.60 times 10 to the negative 19 coulombs. So the charge on 1 electron is 1.6 times 10 to the negative 19 coulombs. Now, because we measure in such small amounts, we also use microcoulombs fairly often. And if you remember from the start of this year when we did the unit changes, 1 microcoulomb means that it's times 10 to the negative 6 coulombs of charge. Okay? So, one more here. All right. So back to this guy then. So my charge on this is represented as Q1 here. My charge on my second guy is represented as Q2. So the law of electrostatics, or Coulomb's law of electrostatics, says that the amount of force between 2 point charges is directly related to the amount of charge on each, the product of them, so I multiply them together, and inversely proportional to the distance between them. So I want that to make sense. If I bring it closer, will I have more force or less force when I bring these two objects closer? More force? Okay, think about it like this. The further we get away from the sun, do we have more or less gravity? Less. So the further we move away, the less gravity. How about from the center of the earth? The further we move away from the center of the earth, do we have more or less gravity?
More.
More gravity the further we get away?
I get to the earth?
Okay, so the center of the earth is holding us here right now, right?
Right.
Okay? The further I get away from it, the less gravity is going to affect it. Correct?
Correct.
Okay, so I have less gravity then, right? Same thing occurs here. So it's actually by a distance squared. So the further you get away, the less force you're going to have. The closer you get to the object, the more force you're going to have. And then we have a constant in here, which is called Coulomb's constant. So we also need to know what Coulomb's constant is. Coulomb's constant, and again, these are all given on your equation sheet. It's 8.93 times 10 to the 9th newtons meter squared per Coulomb squared. Okay? So that's Coulomb's constant. Now, when we do this question, when we do these questions, your charge has to be in coulombs because your units is coulombs for your constant. So you need to always change microcoulombs to coulombs. Alright? So let's look at a quick example question. So this is on page 389. Find the force between charges, 100 microcoulombs and negative 50 microcoulombs, located 50 centimeters apart in the air. Alright. So again, I'm looking for force. Q1 is given as plus 100 microcoulombs. So I'm going to change that to coulombs right away. Q2 is negative 50 microcoulombs. Okay. So one's positive and one's negative. Do I have a force of attraction or a force of repulsion here? Force of attraction. So what I want you to do when you're doing the math in this, I do not want you to add negative signs in. Do not put negative signs in. Okay? Just right at the end, because force is a direction component, you have to put attraction or repulsion for this. And how far apart are they? Again, change to meters, 0.5 meters. Okay, so force equals, get out your calculators. We have to work with our exponent buttons here. Alright, punch that into your calculator.
I'm a little bit blind. What's the second number saying? 100 or
100 times 10 to the negative 6.
Thank you.
Yep. So again, you want to use that exponent button on your calculator.
Okay,
Okay, go
the
ahead.
answer 178.6.
Agree or disagree? Jake, you got that? Anybody not get it?
I got 1.786 times 10
Times 10 to the power of 14.
Are you using 10 or using the exponent button?
exponent button.
You still got it on there?
Oh, I just
Okay, put it in, let's see. Times, negative 6. Divided by. I always leave it on there so I can look. I'll have to do that after. I'm not sure. I don't know what you did wrong. That's how you
I worked it out the same way.
Okay. Maybe not. Oh, I see here. Okay, I'll look at it after. So it looked like it was right, but. Okay, there's one last thing that we need to do, and then I'm gonna give you some questions. Sorry, back to this. Any other questions? Anybody not get it? Yeah.
I got it, but you did say not to put negatives in, but then you.
No. Negative in front, this negative right here.
Oh.
The one that's in front of the 50. Because it's given in the question as a negative 50. Okay? So my final answer should have been this and this.
So if it's a negative number, you attract positive or repulse. You just always.
Yeah, but if they're the same signs, then they'll be repulsion. You say they repel. So if they're both negative or both positive, they repel. If they're positive and a negative, you just put they're attracted.
Okay.
That's it. Okay? Any other questions about this? All right. Electric fields. So I already made mention of this. The concept of a field of force will be helpful as we consider the region surrounding an electrically charged body. A second charge brought into this region experiences a force according to Coulomb's law. Such a region is an electric field. An electric field is said to exist in a region of space if an electric charge placed in that region is subject to electric force. So, thank you. Okay, so you look at this right now. I have this electric field of force around here. An electric field exists if I bring another charge into here. Alright, so it says a second charge is brought into this region and it experiences a force moving it. So either the force is moving it this way or the force is moving it that way, depending on what that charge is. Okay? So to calculate that electric field, now we have to make, I'm going to give you an equation for electric field right now. I'm going to give you a second equation for that tomorrow, which means the same thing but has a difference of units. Alright, so to measure the amount of electric field in a region, I take the force around that electric charge and divide it by the charge itself, the amount of charge on it. And my units in this case are newtons per coulomb. Right? Again, you want to use coulombs and not microcoulombs when you solve for the electric field force. This is what we call electric field intensity. So this is at the top of page 392. Electric field intensity. Okay? The electric field intensity at any point in the electric field is the force per unit charge at that point. The electric field intensity has the dimensions of newtons per coulomb. So we'll look at one quick example question. A charge of 2 microcoulombs is placed in an electric field and experiences a force of 0.08 newtons. What is the magnitude of the electric field intensity? I need to find E. So 0.08 divided by 2 times 10 to the negative 6. Punch that into your calculators. Get 40,000 newtons per coulomb, right? Okay. All right. Very straightforward, very simple so far today. We only add a little bit into this as we go through electrostatics, but I think you're going to find this one of the easier units that you're going to do. And it has nothing to do with anything that you've done to this point. This is completely different from anything you've done so far. All right?
Praise the Lord above.
Sorry?
Praise the Lord above, it's easy.
Yeah. Okay. You need to complete all of the Group A questions on 392 and 393 and do all of the problems. On page 393. Okay? You have the rest of the period today to do that.
Can I go to the bathroom?
Yes. Okay.
Can you go do that?